look at the Zig language and compiling to WebAssembly, WebAssembly is a format that can be run in web browsers and also on the server. Here we're going to make a very simple state machine. It's incredibly so simple, it's like a light switch. So here we have two states which are stored as a integer, and that integer can have one of two values, either a 0 or a 1. And then the switch can be flicked, which changes its state. And you can see here in this logic, if it's currently 0, it becomes 1, and otherwise it must be currently 1, and it becomes 0. When that happens, we just record there was a change that happened. So in the Zig language, we can define structs, which are higher level types that encapsulate other values. And they also have methods. So you can see the flick method, and then this next method. This next method accepts the current switch that's being talked to, and then a string, an event name as a string. And so we see here that if the string that is passed here is equal to the string flick, then we go ahead and call our flick method. And then here we make some of this stuff public. So here is a variable for the current switch, and then we make that public to the outside world, where we let you look at the current change count for that switch. In Zig, you can see that we can test, write our little unit tests right in the same source file. I don't have to have a separate file for this. So you can see here I'm just calling this method, this function that was exported, calling the flick function, and seeing that the behavior is how I expect. And you can see that we're seeing it go from 0 to 1 to 2, and that's from this line here, incrementing the value. Here's our flick method that basically says, hey, with the current switch machine, call flick on it, and then that will return the machine with the new value, and so we store that in current again. Again, you can see a test of just this method here. And here's a way to make this next function available to WebAssembly. So we have to do some sort of voodoo with the types that is compatible in a, I think compatible in a C-like manner, which WebAssembly expects. This strange syntax here means that it, like C, the string must end in a null byte, or basically a 0, for it to know where that string ends. And finally, we have one more function which returns the current state. Publicly, this underlying value of 0 or 1 isn't helpful, and also isn't what we want available as a public interface. So here you can see that if it's equal to 0, we return the string off, and otherwise it must be 1, and we return the string on. So we can compile this using the Zig command line utility. It's incredibly quick. So you can see here we target WebAssembly. The current spec only has 32, is standardized around 32 bits. You can have this high level WASI standard for things like reading files and so forth, but our thing is so simple, we just go with the freestanding version, which makes it very lightweight. And so that spits out a WASM file with this name here. So if I look at that, you can see that that produced a file that is 334 bytes. It's incredibly tiny. To compare, I've created a JavaScript version of this same idea. And you can see that here. So it exports a function that is basically the same thing as our struct, has the two variables inside that are very similar. Here we store the current state as a string, and we have a similar logic here. So we can get the current value, and we have a method to send the next event, and you can see it detects if it's flick or not, and does the same logic. So if I compare, this is not minified, but you can see it's a little bit larger than my compiled WebAssembly. Let's look at it if it was compiled. So 195 bytes, so the JavaScript version is actually smaller here. So I have another version of this same state machine written in Zig, and it's this is actually the original version that I wrote. I went back to create this sort of more primitive version, where I think in terms of unsigned integers and so forth. And here I'm going to use some of the more powerful features of Zig. So the logic here is largely the same, but I'm able to use some of the higher level Zig features. So one of these features is enum. So instead of having a integer, and I think of my state as being 0 or 1, I have two explicit states, off and on. In the same way, before I had to create a string for my different events. This thing only accepted one event, which is flick. And so it would be nice to create a concept for that event, and here I can use an enum for that as well. And then here in my logic, if you remember previously, we had checking if it was equal to flick, and then inside the flick method, we changed the state and incremented a value. Here I've just on the event itself given a event that is being sent or received, and then given the current state, what is the new state. And so here for flick, you can see that we then switch on the state. If the state is currently off, we go on. If it's currently on, we go off. So that's encapsulated in this event. Then further down, we have these same two member variables or properties or instance variables, whatever you want to call them, the state. And here I get to use my state enum. And because the change is just a integer that gets incremented, that remains the same. And then I have a method here to that accepts an event, and it ends up calling the transition method that you saw above on that event. So I'm not just thinking in terms of primitives. I think of more of these sort of like object-orientated or value-orientated things with methods on them. And then here you'll notice that I'm no longer comparing strings manually. I'm using something called a comptime string map. And so in that map, like any other hash table or map, I look up for a given value, for a given key, what is the value? And so I'm saying, hey, if look up the value for the key that's the event name. If that exists, this will be truthy, and then we'll get the event value that it found. And then I call the transition method, which you then saw come through here. So how does this, what's this comptime string map? What's this events thing? It's a map that maps from strings to my type here, which is event. And here I have one entry. The key is the flick event turned into a string, courtesy of the tag name helper from Zig. And then the value is the event.flick event, this thing up here. And you can see the code below is pretty much the same, except instead of starting off as 0, we get this more richer off. And here's the thing that's really exciting to me. So you saw this thing get built before. So here I'm going to build the new one. And so what I'm doing is I clear my Zig cache to get a clean build. I ask Zig to build my this version of the state machine to compile out. I then run that same list command to see how many bytes it is, 334, and I generate a SHA-256 hash. And so this uniquely identifies the produced WebAssembly file. A different file that differs in just 1 byte or even 1 bit will produce a different hash. So if I see the same hash here, I know those two files, the two contents of the two files are the same. So what I'm going to do here is compile this version here, which has the richer constructs using enums, and then the simple version, which is sort of very bare bones, and compare the two. And this is what has made me really excited, is that they both produce a file that is 334 bytes, and they actually produce the same output. So what is happening here is that Zig is able to do a lot of the, I'm able to use higher level concepts. You can see this enum is actually backed by an unsigned 8-bit integer. And it sort of strips all this higher level stuff that made this code nicer to read and nicer to write. And it stripped it back into basically the same code as this very simple version. And that goes as far as this comptime string map. So what this comptime string map is doing, as it suggests in the name, is at compile time, it's creating this map, but it only really needs to exist at compile time. And so this call here to that instance can get compiled away and essentially gets compiled down to the same check of the raw memory. But it's in a much nicer API. So you saw that the JavaScript version was actually a little bit more lightweight, but I think there's a lot of things here that are interesting. I think Zig is a really interesting language. It has a lot of sort of semi-powerful features. I don't feel like it's going to take months and months to learn. And it gives you type safety. And the compiler is really nice and fast. And the other thing is WebAssembly, I think, is really interesting, where you can create these little modules. They called WebAssembly modules, and they can be downloaded like any other JavaScript, but they offer different trade-offs. and including allowing me to write in a different language like Zig. And I'm going to explore this space further in the future. So you might be wondering, how do you run this WebAssembly thing? I've got two examples here. One in Deno. This sort of maps to a lot of the same functionality that you'd get in a web browser. So this WebAssembly.instantiate is something that you can look up on MDN. So this is the MDN docs. And so it's the exact same API as that I'd get in a web browser. And here's just a little bit of Deno nicety to read that WebAssembly file that Zig created. And this environment thing is actually not needed, but we basically instantiate, we create an instance of our WebAssembly module. And then you can see interacting with it is not as nice as if it was in JavaScript, but you can create helpers for this and create a lightweight layer in between, so you wouldn't have to access the buff of the raw memory every time. But if I run this, you can see that what I'm basically doing is calling those methods that were exported, so get, change, and flick, and I'm able to see interact with this instance. It's got mutable memory, and so I can look at the current value. It's currently off and has made no changes. It's 0. And then as I call the flick method or function, however you want to think of it, it's incremented that number and now it's on, and then again it's incremented again and now it's off again. You can see here we have to use the text decoder and encoder functionality, which is also built into web browsers, to turn that string into a JavaScript string. So turn that raw buffer of bytes that WebAssembly, that's all that WebAssembly can really understand. It just thinks of everything as a byte or an integer or an array of those things. And you can see here we find that null terminating byte, that 0 that determines the end of the string, and then we read a subsection of the full memory corresponding to that location of the string and decode it because it's UTF-8. I've also ported this to Bun, and you can see Bun is sort of in the same vein as Deno. How you read a file is slightly different, but basically all the other code is the same, and you can see similarly very fast, and you see the same result happen. So I've got a few other ideas in this repo, so I'm going to explore those in future videos, and I've also been exploring state machines a lot, so I hope to return to that as a subject.